Hello and welcome to another episode of Paper Talk. Today we have with us Ankit Kumar Gupta, who completed his MSc from Deen Dayal Upadhyay Gorakhpur University. Currently, he is pursuing his PhD at Department of Organic Chemistry in Indian Institute of Science, Bangalore. Today, he will present mechanically interlocked molecule, Rotaxanes and Catenanes. So, Ankit, welcome to the talk, and the screen is yours.
Thank you, Bhaiya, for your kind introduction. So, hello everyone. Today we'll be discussing about mechanically interlocked molecules such as the rotaxanes and catenins, starting from their synthetic strategies to some of their application. So, this is the contents I am going to discuss today. So, firstly, I'll introduce the term topological isomerism as well as the mechanically interlocked molecules. Then I'll move to the rotaxanes and catenins, starting from their synthetic strategy to discuss how chirality is existing in between them, and then I'll move to some of the application, and then finally we'll conclude our topic. So stereoisomerism come in a picture when there is a two molecule is having same molecular formula, same atom to atom connection, but the different spatial arrangement. As we can see here, suppose if these two enantiomers are like these two molecules are enantiomer, so one having the R conformation, another will having the S conformation. They are having the same molecular formula, same atom to atom connection also, but the spatial arrangement are going to different. Suppose in another hand, we are having a class of molecules such as the cycloalkane, knotted alkanes, as well as the interlocked cycloalkane. So all are having the same molecular formula, same atom to atom connection also, but as we can clearly see, they are different, like they are different in a global arrangement. So these type of molecules are classified as the topological isomerism. This type of phenomena was firstly intuited by Richard Martin Willstetter, who won the Nobel Prize in Chemistry in 1915 for the work on the chlorophyll. During the synthesis of some polymers, he observed some formation of some high molecular weighted polymer which was uncharacterized. But he intuited the formation of the high molecular weighted polymer may be arise due to the interlocking is going to be formed in the system, and hence that can form the interlocked structure as well as the knotted structure. Later on, E. Wasserman has came with a different classification of the topological isomers, and he introduced the term chemical topology, where actually topological isomerism existing in between the chemical structures. So he has taken up this catenins, knot, and Mobius strip, and he classified this as the chemical topology. Later on, another type of existence of another type of molecules also come in a picture, where this rotaxane, where this circular ring was threaded by this dumbbell, as well as the pseudo rotaxane, where these two stoppers are absent in the present, like in rotaxane. So they are classified as a pseudo rotaxane. So all these three molecules come under the mechanomolecules category. But including this rotaxane, pseudo rotaxanes, catenins, and not, they are broadly classified as the mechanically interlocked molecules. They are called mechanically interlocked molecule because they are interlocked without presence of any chemical bond. Later on, pseudorotaxane can also be considered as the host guest chemistry or the host guest molecule in the supramolecular chemistry. As we can clearly see, this linear thread is just embedded in the circular ring. So it is a kind of a host guest complex, which is known as the pseudorotaxane. These are some real life example we are facing where the interlocking is present, and we can just relate this physical structure with the chemical structure. So now moving to the catenins, which is actually Latin term, which is derived from the word catena, which is having the meaning of chain. So a molecule with two or more interlocking ring shaped component parts are classified as the catenins. Here are some catenins which is classified as is N-catenins, where N is nothing but it is representing the number of ring is present in the molecules. Olympic symbol is also catenins, which is actually known as the Olympian, and that catenin molecule is also synthesized now. So for proving the existence of this type of interlocked structure in the chemical society, it was needed to prove the existence of this type of molecule chemically, and the characterization of this type of molecules are also required. So for doing for proving the existence of interlocked structure, E. Wasserman has proposed the first experimental observation to prove the existence of catenated structure. So what he have done, he has taken one 20-membered cyclic alkane along with this 20-membered linear diester, and he performed the acyloin condensation reaction, which is a very well-known reaction of diester moiety to form this alpha hydroxy ketone. So he thought, apart from the simple cyclization, since this molecule is a linear, so it can threaded in this 20-membered cyclic and can penetrate from one side to another side, and then after it can go cyclization, which will give actually the two catenanes. So he detected it and he characterized it, and he further confirmed it by some experiment where he has done the cleavage of this blue ring. So once he has done the cleavage of this blue ring, he got again this 20-membered cyclic structure isolated. So from where he concluded there is the existence of such type of molecule where this blue ring as well as the red ring are in contact with each other, and this interlocked structure may be the most plausible pathway. And from here he proved there is the existence of this type of catenated structure. But this process limits this process is having some limitation, because firstly this is a statistical method. Statistical method means here is the 20-membered carbon ring, and here is also 20-membered carbon ring. It means the number of atoms are very high, and the conformation number of conformation which will exist are very high in the number. So there will be the very less amount of this catenated structure formed, and all the observation he has proposed on the base of the mass spectrometry, which is not actually the proof of the existence of the catenated structure. To overcome this limitation, Schill and co-worker has developed a new template synthesis in 1964, just after the 4 year of the first proposal of this interlocked structure. He has started from this dialdehyde dimethoxyaryl, and firstly he has done the Wittig reaction to form this diester moiety. Later on, he has reduced this unsaturated double bond, both the unsaturated double bond, to get this saturated linear chain, and then he has done the lithium aluminum hydride reduction of this diester to corresponding alcohol, and in presence of HBr, this alcohol will convert to the alkyl halide, and in presence of cation, that alkyl halide will convert to the alkyl nitrile. Later on, under the base hydrolysis, this two chain is going to be cyclized to give this ENSA derivative, and which here this dimethoxy can be converted to the free OH, and this will be the ENSA catechol derivative. Later on, since these two OH is free, this can undergo the ketal formation reaction, and it will give this ketal protected moiety. And then after, starting from this ketal ENSA compound, he has done the nitration reaction, which will selectively will occur at this position of the benzene ring, and this can be reduced to the aniline derivative. Now, since this is basic, using the base, this center can be deprotonated, followed by the nucleophilic attack at this center. So from top side and the bottom side, this will give this very complex moiety, which is actually one step away from giving this two catenanes. So in presence of iron catalyzed conversion of aniline to quinones, actually it is giving the alpha hydroxy quinones, which is actually a catenated structure, and it was a very remarkable strategy to prove as well as the chemically characterize every step of the reaction by spectroscopic techniques, and for proving the real existence of two type of catenane. But although it is advantageous over the statistical method, but since all these processes are containing very large number of steps, so scale up is challenging for screening this type of molecules in a further application in the real life. So now it is required to develop some method with a very low number of steps and with the very high selectivity and the yield. So in the meantime, David R. Macmillan of the Purdue University was actually working on this 2,9-diphenyl 1,10-phenanthroline ligand, which is also known as a DPP ligand. So he was studying this particularly this ligand and their copper complex for the photophysical properties, some transitions in the metals, some photochemical properties. There was screening this molecule as a photocatalysis, they were also applying this compound in the electrochemical properties as well as in the water splitting reaction. So he thought if they will have this two free OH group at the terminal, they found this ligand is working good in their condition. So at the same time, they thought if they are having this molecule and if they can do the Williamson ether cyclization reaction in presence of this long chain halide compound, so that can give the metal bound catenated structure. And since this is metal, if we'll subject this metal to form some strong, very stable salt, so that will actually take out this metal from this center, and that will be actually the catenanes. And they have achieved this catenane synthesis only just in a 3 step, and this was a remarkable attempt and the achievement in the field of interlocked structure. So from here, although this molecule we can see has having the plane of symmetry, but depending on the particular orientation as well as the substitution, this catenary structure can also show the phenomena of chirality. So as we can see, both the ring are having the plane of symmetry, no doubt. But once the interlocking will happen, we can clearly see they will exist as their non-superimposable mirror images. So there is a chirality in between them. And this type of molecule was synthesized recently, just 3 years ago in 2022, by the Goldup and co-worker, where they have achieved very high silencio selectivity for the synthesis of interlocked catenanes. So with that, we are moving to our second molecule, which is actually rotaxane. So rotaxane, also a Latin word. Rotaxane derived from the Latin words, which is meaning wheel and the axle. And this is a comprise of the molecules which is having the axle-like dumbbells, which is actually stoppers that are too bulky for the slippage of the rings, so that this ring cannot be slipped out from here. Otherwise, that will not be a interlocked molecule. That will be a two different separated moiety. So for synthesizing this rotaxane components, so for synthesis of this rotaxane complex, they have taken the help of a very common strategy, since the crown ether complexes are very well known for the stabilizing these cations. So they are very specific for the cations. So 15C5 is a very well known for stabilizing the sodium. 18C6 is known for the stabilizer of potassium. Same for this cesium as well as some different metal F block elements and their cations. So they thought if they are having some electron-rich ring and there is a cation in a close proximity, that will immediately move to form the bond which will stabilize actually this cation. So by taking the help of this strategy, they have designed the synthesis of the rotaxane, which is actually the threading stop ring strategy. So firstly, what they will do, they will have this negatively charged supramolecular ring and one cation which is threaded on this linear moiety. So one thread will go inside to drive it by the stabilization, and then they will having a very big stopper which will actually bind at the both the terminal. And now here we can see this molecule is interlocked and this ring cannot be flipped off from here. So they can very good strategy, like this can be a very good strategy to achieve the mechanically interlocked molecule. But they are also having some problem, because driving this linear thread as well as this supramolecular moiety to find to give the pseudo-rotaxane complex is actually an equilibrium, and it is also the statistical control, whatever we had discussed previously. So later on, the modified strategies also come in a picture, where what they can have one big stopper at the one end from starting and one very small stopper at the one terminal. And once they will treat it to under certain reaction condition, it will form the pseudo rotaxane. And then after some chemical triggering, they can expand this ring, this dumbbell, this terminal, so that now this ring cannot be flipped off from here. And this strategy was applied and was successfully achieved the synthesis of rotaxane in 2007. Firstly, they have prepared this ammonium salt, ammonium hexafluorophosphate salt, and then after, in presence of this benzo crown ether, in the presence of nitromethane as a solvent, they can drive the formation of this pseudo-rotaxane complex, actually, which is stabilized by the hydrogen bonding, which hydrogen bonding network we can see here. This NH2 plus is actually doing a very strong hydrogen bonding network with this all the oxygen present here, and end bonding is favors the equilibrium toward this right side. And then after 3,3 sigma tropic reaction in the presence of heat will occur actually, which is increasing this very small. If we can see, this is very small initially. Now it is increased to the 7-membered ring, and which is actually found to be a stopper for this reaction. And hence they have achieved the 86% of yield of the rotaxane. Another strategy is also in picture, just opposite way of the last strategy. Instead of this initially in previous strategy, they was starting from this initially small stopper. Now if they have both the stopper as such in the axle, but ring size was initially big, and then after some chemical triggering, if this can shrink the ring size, that will also give some mechanically interlocked molecule, because again this ring cannot be flipped off from here. This strategy was also applied and successfully achieved the rotaxane synthesis. So firstly they have chosen this Saline derived this benzo crown ether, which is actually again forming this hydrogen bond with this ammonium moiety to drive this equilibrium toward the right side. And then after they are adding some metal, which is binding actually at this 1, 2, 3, 4 sides. So for what is happening, firstly the chemical space was from this bond to this bond. This has to hold this linear chain, but now if we'll see this chemical space is from here to this metal, it means the ring is shrink, and hence this is actually a mechanically interlocked molecule. Another strategy is also developed where the clip formation can be done around the axle. So starting from this linear chain, firstly this, since we can see this is the aldehyde, this is also aldehyde, and here is the free NH2 from the aniline. So aldehyde and NH2 in presence of the catalytic amount of acid is very well known to form the imine formation reaction, and that reaction is very spontaneous at the room temperature. So what can happen, firstly this NH2 is having two. NH2 is actually, this H is a very polarized bond, which will do the hydrogen bonding with this oxygen, this, and oxygen, and along with this nitrogen also. So what will actually happen? Firstly, this hydrogen will invite this moiety as well as this moiety around the axle, and then after, once they will come in a close proximity, the spontaneous imine formation reaction will happen, and now we can see the complete formation of the ring. And hence this imine are very known to be, like, generally imine are known to be very unstable. So what they have done, they have reduced this imine to amine, which will actually which is actually found to be very stable. So they have also achieved the rotaxane yield of the 58%. So apart from this, all the methods we have discussed previously, they are actually the statistical method. So one thing can also be done, starting from this ring as well as the one side dumbbell, it can form the pseudo rotaxane complex, and then after covalent dropping, like the metal catalyze some reaction or some another covalent bond formation reaction can be done to trap this terminal, which is actually again the interlocked molecule, where now this ring cannot be flipped off. This is also achieved by taking this ammonium salt in presence of this dibenzo crown ether in DCM as a solvent. This will actually form the hydrogen bonding network to drive the equilibrium forward side to give the rotaxane. And since this is alkyne, the alkyne moiety can subjected to Sonogashira coupling reaction in presence of aryl iodide, which will give actually this attached moiety, which is now which was previously stop that was not actually stopper, that was very less hindered. Now it is very hindered, and then it is acting as a stopper to form the rotaxane in a very good amount of yield. So by overcoming all the strategy, some active template method to synthesize the rotaxane was achieved. So by using very clever ideas, since metal transition metal, generally palladium, iron, and all are known to be from the covalent bond, starting from the aryl iodide or any cross coupling partners, such that the Suzuki coupling and different palladium catalyzed reactions. So they have designed the supramolecule in such a way that metal can bind here, and that metal will lie inside the ring. And if that metal will lie inside the ring, that can actually catalyze the bond formation reaction of the two cross coupling partner to give the rotaxane in a very good yield, and they have achieved in a very successful manner. So if we will see the catalytic cycle, so starting from this ligand, firstly metal is actually binding to form this complex, and this metal is lying inside the cavity of the supramolecule. And then after in presence of baits, this amide will got deprotonate, and that will substitute this halide ion, which is actually a bromide or acetote or iodide. That will substitute by this generated amide anion, and that will bind to copper. And now since three bonding site is saturated, one more bonding site can also happen, and that will happen whenever this copper will go oxidative addition within this aride iodide bond to form this pentacoordinated species. And from here the reductive elimination will happen to form this between this bond and this copper nitrogen bond to reductively eliminate the copper, as well as form this bond between the carbon and nitrogen to generate the rotaxane in a very good yield. And this was the first strategy of the using active template method with where they are using some metal catalyzed reaction to synthesize the rotaxane. Although both of the component of the rotaxane, the axial as well as this supramolecule cycle having the plane of symmetry, so they will separately will not exist as the enantiomer of each other, or there will be no chirality in the different component. But once the interlocking will happen, that will actually give the rotaxane, and hence we can clearly see they will exist as their mirror images. And hence there will be there are some examples which is synthesized by the Goldup and coworker recently in 2022, where they have achieved the very high enantioselectivity of the rotaxane. So moving toward the enantioselective synthesis of the rotaxane, firstly, it is very difficult to control the enantioselectivity because there is a reaction of the supramolecular component with the two different coupling component. So controlling the enantioselectivity generally requires the phase discrimination. But controlling phase discrimination in such type of the supramolecular system is a very challenging, and it was a completely unbelievable that the recently the enantioselective synthesis of the rotaxane was achieved. So firstly, this is the typical strategy for the synthesis of rotaxanes. What we have developed, what we have discussed so far is firstly they are taking this ligand a ligand bound supramolecule where this metal will bind, and then after the click reaction will happen, or simply the alkyne azide cyclization reaction will happen inside the cavity, and that will generate the rotaxane. And this rotaxane formed can be simply detected by the hydrogen bonding, because once we will do the uh, click reaction without presence of this supramolecule, that will form the triazole moiety, and this proton chemical shift will be different. But once the hydrogen bonding will happen with that, now this will having the different chemical shift, so we can simply detect the formation of rotaxane. So recently what uh, scientists thought that how we can develop the synthesis of the chiral rotaxane. So they thought if they have the different substituent on this alkyne partner, then what will happen? This will form the distereoisomeric complex. And since diastereomer having the different physical properties, different chemical properties, this all because of their different stabilization or the different destabilization energy. So what they thought, once we can form the distereoisomeric complex, then it can go the diastereoselective reaction. So once we can carry the stereoselective reaction, it will be easy to convert it to certain enantiomeric access by cleaving some bonds. So here, recently in 2018, the Goldup and co-worker has successfully achieved the stereoselective synthesis of the chiral stereoselective synthesis of the rotaxane by using the alkyne azide cyclization reaction, where they have done some where they have used some amino acid derived azide as well as a modified version of the amino acid, which is actually an NC pure in nature generally, and which are very cheap. We can avail it from the nature. So once they have achieved the distereo selectivity, now distereo selective reactions can be lead to NNC selectivity. How? So for that we have to remember the Evans auxiliary strategy. So firstly, attach one chiral auxiliary to the achiral substrate to modify the substrate. Once the substrate is modified, you have to carry out an distereo selective reaction to induce the distereo selectivity. And once the distereo selectivity is good, you can remove the first step auxiliary to give the NNC induced product. Using the exactly same strategy, Goldup and co-worker have developed the first synthesis to the chiral Rotaxane. So starting from this azide and this alkyne, which is actually will form the diastereomeric Rotaxane. Once the diastereomeric Rotaxane is formed, this hydrogen bonding can exist at this position also. This hydrogen bonding can exist at this position also. But problem is that this ring is locked at this position. Once we will once we will move, once we will allow to move this ring across the axle, rapidly it will shift from here. Because you can see here is the steric is more. So once the hydrogen bonding is destroyed, that will immediately jump to this position. So for doing so, we can here see a removal of this PMB group. PMB is actually para-methoxybenzyl group, which is actually a very big group. So once we will remove this one, this blue ring will shift immediately to this position. So that is actually happened in presence of trifluoroacetic acid. Once we have removed this PMB group, this ring is shifted to this position. And firstly, this was having this some configuration, and this configuration is also same. But the very clever strategies was that once we can remove this triazole moiety, once we can remove this triazole moiety, so firstly it is acting at a diastereomer because one chiral center is there. So chirality is coming from two positions. Firstly, one center is there, as well as the chirality is coming from this one. So if you anyhow remove this center, so only one enantiomer will be there. So they have removed by this ester hydrolysis. Once you will do the ester hydrolysis here, that complete moiety will move from here, and that will exist as a pure enantiomer. And this was a very good achievement for the synthesis of the chiral Rotaxanes. So apart from all the discussion, this is time to discuss some of the application. So simply this Rotaxane can act as a catalyst, which is quite obvious because these are having the very high chemical space. So that can act for the phase discrimination as well as the photocatalyst as well as some different drug delivery system. So here is one typical example where they are doing this beta addition of this nucleophile 1,3-dicarbonyl compound to this beta position. But controlling the stereogenicity at this position using this catalyst 1 or 2 is a very challenging, because once catalyst will bind with this aldehyde, this steric controller will lie far apart from this beta position, so it is very difficult to control the selectivity. But using this rotaxane complex, which is actually this ammonium ion, once we will have the strong base, this center will be deprotonated, and once this center will be deprotonated, this hydrogen bonding network will be destroyed, and this red ring is now free for moving from all the apart from this linear thread. So once this positive center will be destroyed, here is a positive center, so this ring will move to here for getting stabilization, because this all oxygen are having lone pair, so these are very electron rich ring. So once it will move to here, this triazolium moiety, it will again stabilize to generate the NH2 here, and that NH2 will activate this aldehyde, and that aldehyde will go undergo iminium catalysis, and now the selectivity was achieved. There, since we can see using catalyst 1 only, we was getting only 2:1 selectivity, almost like 68 32:68. In the case of catalyst 2, we was getting little bit little bit more selectivity, but again in the using catalyst 3, we was getting the very rapid rate reaction as well as the very good enantiomer selectivity level we can achieve here. This is also an example of the switchable catalysis. So once you will deprotonate this one, this moiety will actually move here. So it is actually a photo, like it is a switch. Firstly, you have to add some base, which will actually add as a switch, that is on off. So once we will add this NaOH, that will deprotonate to generate this NH2 NH group, and this ring will move to this triazolium moiety, which we have discussed previously. Here is the some another application of the rotaxane. So firstly, what is forming generally, this triphenyl phosphine complexes are not very stable. So starting from this two component, we will get this triphenyl phosphine without gold chloride. If there is a triphenyl phosphine, so that is a very prone to go for the oxidation, that will form the diphenyl phosphine derivative. But they have formed this gold complex, and here this are found to be a very stable. And this rotaxane is used for getting selectivity in the cyclopropionation reaction, which is also O'Hare-Humira cyclopropionation reaction. So using this propargyl alcohol derivative as well as the styrene, they can achieve the cyclopropylation reaction where the cis product they are getting in a 16% one exclusive manner. So using normal triphenyl phosphine catalyst, they are getting only 5:1 selectivity. Here they are getting 16:1 selectivity. And here is one example of the two catenanes where it is acting as a photocatalyst. So what will happen firstly, since we can see this tetrapyridinium moiety is present here. So presence of this tetrapyridinium moiety, it is actually making this site electrophilic. So TBI, it means the tetrabutyl ammonium iodide. This will having this I minus source. So I minus will attack any of this position because all four are exact equivalent, chemically equivalent. So once they will attack on any side, this chain will open to form the linear ring. This ring will open to form the linear chain. That linear chain having the very large number of cations, since it will attack here. This 1, 2, 3, 4, 4 positive charge will be there, and these rings are very electron rich, so it will form the pseudo rotaxane, whatever we have discussed previously. So that will form the pseudo rotaxane, and once the pseudo rotaxane will form, there is this aromatic moiety which will do actually the pi stacking, and due to pi stacking, these two terminal will again come close, and that will again cyclize to generate this 2 catenane. And since one within the one molecule, one electron rich moiety as well as the electron deficient moiety is present here, so it is very easily it is very easy to do the transition or the charge transfer between the molecule, and that will generate the radical cation anion, and that can act as a photocatalyst. So it's using this catalyst, they have achieved the successful selective oxidation of this dimethyl sulfide amino acid to this dimethyl sulfoxide amino acid. So with that, we are now at the conclusion. So firstly, we have seen the term topological isomerism and what is the mechanically interlocked molecule, how they are arising, and further their classification, the chemical topology, mechanico-stereochemistry, and all. And after that, we have seen the chirality and firstly, we have seen the synthesis of the rotaxanes and how the chirality is existing in between them. And that after, we have also seen the chiral synthesis of the rotaxane. After that, we have seen the synthesis of catenanes and the existence of chirality in them. And then finally, few of the application we have seen of the mechanically interlocked molecule in the asymmetric catalysis. So for that, there are some current research are going on. So till now, there is a very less study in the field of enantioselective synthesis of the rotaxane as well as the catenanes. So under metal catalysis as well as the organocatalysis, there is no such report for the enantioselective synthesis of the rotaxane. And by just varying this oxygen to nitrogen, we can also think of do the forced phase transfer catalysis under the acidic medium condition, which can actually induce the enantioselectivity activity. And with that, I'll thank you all for the listening the talk. Thank you.
If you enjoyed this session, don't forget to like, share and subscribe. We'll meet you in the next episode, next session. Thanks for watching.